So that last problem we did was a confidence interval, and I did the confidence interval without even showing you the formula, but here's the formula. So we're familiar with the notation already, the p-hat business. So p-hat 1, p-hat 2, and then they have basically, if you compare it to a confidence interval that we had from way back when we did the confidence interval for proportions, it's really a p-hat minus e less than p less than p-hat plus e, except instead of just a regular p-hat or p, it's a p-hat 1 minus p-hat 2, and then the p got replaced with p1 minus p2, the difference. The margin of error looks fairly similar. It's a little bit different, but it's the same business. If you compare it to the margin of error from before, it was z sub alpha over 2, the critical value that we would have found, and then there's p hat q hat divided by n. This time they have p hat q hat, or p1 hat q hat 1 divided by n plus p2 hat q2 hat divided by n2. So it really, literally, just an extension from what we've been doing before, and it still works for us. So, okay. All right, let's go to the next section. Again, if you did just download the PowerPoint, you can take a look at all this stuff. Let's look at the next section, and this time it's looking at finding the hypothesis test, or doing a hypothesis test in confidence intervals for two means or two samples. Now, 9.3, this section talks about dealing with two samples where you have independent samples. 9.4, we'll see, is going to deal with two samples when the samples are paired. Okay, and so we'll take a look at what those what the distinction is between those two different scenarios, but we'll focus on this idea of having two independent samples for now, because even in this section, this is broken down, or the book breaks this down to 2 or 3 options. We're going to stick with just 2 options. The third one, I'll mention it, but it's not practical, and so it's not really necessary for us to deal with. So here is the first part we're going to assume, and this is the one that comes up the most. And if I were to ask you a question on the test, I'll probably be asking you a question that's more focused on this. So independent samples, and sigma 1 and sigma 2, the population standard deviations for the two different populations that we're dealing with are unknown, and we're going to assume that they're not equal. Since we don't know it, there's no way for us to assume that they are equal. It doesn't make sense for us to assume. But that's the other part that I eliminated from this section, and I don't want to talk about that because it's just going to get confusing. So we'll just assume that they're not equal, and the fact that they're not equal, there's going to be an option in your calculator that's going to ask you something, and that's really directed towards, are you assuming that your sigmas are equal? And we're always going to say no. Okay, so just like section 8.2, section 8.4, where you don't know anything about sigma, we use a t-distribution, so we'll also use a t-distribution here. They start off this section with a definition that's going to help us distinguish these types of problems versus the types of problems in the next section. Two samples are independent if they are not related. and 2 samples are dependent or match pairs if the members of one sample can be used to determine the members of the other sample. Okay. So I don't know if these definitions make sense right now, but hopefully when we go to the next section and talk about dependent samples, and we come up with a few examples about them, then they will be clear. All right, we have our standard requirement business. The last section, they kind of put the requirements 2 and 3 together. The samples are independent and are simple and random, but here they split it up again. But more importantly, we're assuming that sigma 1 and sigma 2, the standard deviations for the populations, for the 2 different populations, are unknown. And since we don't know anything about them, we're going to assume that they're not equal. And then we want either or both. The 2 sample sizes are large enough with n bigger than 30, or the 2 samples come from a population that is normally distributed. So these are requirements that you would normally check in a real-world situation. For our class, we're just going to assume that it's true, unless the homework asks you specifically to check. All right. So here is our test statistic, the formula for a test statistic. In Chapter 8, we got introduced to a test statistic where we're testing the mean, and the sigma is not known. And I think that was section 8.5 or 8-5, where we got reintroduced to the student t distribution. I don't know if S was squared there. Anybody have the formulas in front of them? Is this S or S squared? From section 8.5. No? Just S without the square? What? Oh, it's not underneath. Oh, the n is underneath the square root. Ah, okay, so that's the difference. Okay, well, if S was squared, then it can go underneath the square root, and then it'll look just like that. Well, it wouldn't look just like that. There's a plus there. But they also didn't mention the possible null and alternative hypotheses. We can do that like we did in the previous slides. So your null hypothesis, your null hypothesis would be mu1 equal to mu2, and then your alternative hypothesis, mu1 not equal to mu2, mu1 less than mu2, mu1 bigger than mu2. So again, you can pair it up with a different null hypothesis, but if you put the null hypothesis to just be the equality, the equal sign, then it'll all work out the same way. This is a 2 here. So this is it. You got your null hypothesis, you got your test statistic to test it, and then you would come up with the same conclusions, go through the same steps. So let's do a problem. Oh, the degrees of freedom. Since they have two different sizes now for the samples, N1 and N2, the degrees of freedom gets a lot more complicated. Well, we can make it a lot more complicated, or we can make it just a little bit complicated. We'll make it just a little bit complicated. In this book, we use a simple and conservative estimate that the degrees of freedom is just the smaller of the two ends, the 2 degrees of freedom from the first sample or the second sample. There is a more complicated formula to figure out the degrees of freedom to use for this, but we're not going to go there. If you decide to use what we've been calling the traditional method, where you have to find a critical value, in order to find a critical value, you need the degrees of freedom, and the degrees of freedom, we'll just use the smaller of the 2 ends, or the smaller of the 2 DFs. All right. And they have an example here where they compare Bonds and McGuire's home run race, but we're not going to do that. We're going to pick another problem from the textbook, and I already picked one, or from the homework, from our section. So, this this question says a randomized trial. Oh, this is talking about a confidence interval. We'll do a confidence interval. We'll do a hypothesis test on a confidence interval. A randomized trial tested the effectiveness of diets on adults among 44 subjects using diet 1. The mean weight loss after a year was 2.8 pounds, and they give a standard deviation. With 44 subjects in the second diet, the mean weight loss was 1.6 pounds. The standard deviation is 6.1. We want to, instead of constructing a 95% confidence interval, let's first do a hypothesis test. And let's see. Test the claim that, what should the claim be? That diet 1 diet 2 was more effective, or diet 1 was more effective? So I think this is a fair statement for our claim, and it's going to make you think a little bit more, because it's not just automatically, the statement doesn't automatically convert to a mathematical statement. So let's say this is our first part, and notice I purposely didn't put a significance level, because if we don't have a significance level, what do? It's assume it's 0.05. So we're going to assume it's 0.05. If it's not given to us, we're going to assume it's 0.05. Quiz number 4 is up already, right? Okay. So that one, I didn't put the significance level, so you have to assume that. All right, let's first collect the information that's given to us. So I guess we should also start looking at deciphering the words, and then figuring out what is the parameter we're testing, if it's 1 or 2 samples and stuff like that. So clearly this is something that has 2 samples, right? So on the side, maybe your little thinking cloud, you think 2 samples. And the statement about the confidence interval tells you that you're looking for the confidence interval to estimate the difference between the population means. So the word means is there. Tested claimed that diet 1 was more effective than diet 2. That has nothing to do with, it doesn't say anything about the means, right? But in a way you have to assume that, because as you're reading this, they give you information about the mean and standard deviation. And testing the standard deviation tests the variance between these two things. And so it would make sense that we are testing the means. So this is mean. And whether you're dealing with one or two samples, if you're testing the mean, one of the criteria is that, or one of the other questions you would ask yourself, do you know the population standard deviation or not? So if you scan through this, we have standard deviation is 5.6, but that must refer to the sample. So we have no information about sigma. Sigma 1, sigma 2, unknown. So these pieces of information, whether you think it or think it and write it down, should be part of your process. Should be something that you should start getting used to, I guess. Like I said, when you're dealing with a particular section, I'm in section 9.3, so I know that I'm dealing with means. But I think it's an important thought process to get these things down so you get used to it after a while. All right, we need to collect some statistics, and we need to identify the first sample versus the second sample. Well, diet 1 and diet 2, I think that pretty much clears out which one is going to be population 1 and which one's going to be population 2. And in testing the means, we need stuff like the X bar, the S, and the N versus the versus the proportion where we need the X and the N. And since there's two of them, we're going to label them sub 1, sub 2, and stuff. So X sub 1, X sub 2 bar, X sub 1 bar, X sub 2 bar, S1, S2, N1, N2. And sometimes you might be given a piece of data or a set of data, a set of numbers, and so you might have to find this yourselves. Fortunately, here they give us that information. Diet 1 has a mean weight loss of 2.8 pounds, standard deviation of 5.6, and there was 44 of them for diet 1. Diet 2, another 44 of them, this time with a mean weight loss of 1.6 and a standard deviation of 6.1. So that is our diet 1 and diet 2 information. Those are all the statistics that we'll need. Usually that would go under step 5 in your process, but if we collect them from the beginning, I think you'll have more confidence to go on with your hypothesis test. And claim, let's just say this is our claim. A diet 1 is more effective. So now this is where it gets a little trickier mathematically. How would we write this? And before you start, I'll say this is a comparison between two means. So I'm going to want to compare the mean from diet 1 versus the mean from diet 2. And diet 1 was more effective. What does it mean for the mean if diet 1 was more effective? Diet 1 would have a larger number, right? A larger mean. So this would be a greater than symbol. All right? So once you get that figured out, you know your null and alternative hypotheses. Mu1 bigger than mu2 is the claim, and since that claim does not contain a condition of equality, it goes under the alternative hypothesis. then your null hypothesis, you can write the exact opposite, which contains a condition of equality, or you can just write equals to. So that's it. Your statement is set up. Now that you have all this information, and we're going to assume that alpha is 0.01 or 0.05, now that you have all this information, let's just go to our calculators and have our calculator do all the work for us instead of that business. So, nope, we're not doing the z-test. So we have two samples, and our sigma is not known, right? So it kind of makes sense for us to use a t-test. So two-samp t-test would be our business.
So we use z
if sigmas were known, yes, you would use the z, and that's the other part of this section. But again, that's sigma being known is not likely in our real world. So we don't have the data, we have statistics that we're about to punch in here. So let's go to the stat side of things, and let's type in all our information. So our x1 bar, if you labeled it correctly too, it makes it easy for you to input it into your calculator. The S1 is 5.6, the N1 is 44. The second mean is 1.6, the standard deviation is 6.1 for the second, and again it's 44. And if you keep scrolling down, we have our alternative hypothesis, which is a greater than symbol, and one more down, this is where do we assume that the population standard deviations are equal? If we assume that they're equal, we're going to pool it together, and that's the pooled yes business. In our class, we will never use pooled yes. So whenever you have a pooling option, just say no. So pooled, no. And if you hit enter or calculate, you'll get your results. And if you scroll down, it'll spit back your statistics that you inputted yourself. Now, why do they do that? Why is that important? Well, it happens so that if you didn't have the original statistics, if you have just the raw data, numbers for the first list and numbers for the second list, then it'll automatically calculate that for you, and that's where it would come out here. But for us, since we've inputted the data, all those things are insignificant. They're just repeated again. So this is what we're working with. Our result gave us our test statistic, and our test statistic is a t-test statistic. So I'll say t is equal to 0.9612 or 3. When your test statistic is pretty close to 0, there's a good chance that you're going to fail to reject the null hypothesis. Usually large test statistics for t, the go further you go out, the smaller the probability values are. So the PV, in this case, what we'll be looking at is 0.1695, 1696. And we got this from two-samp t-test. I forgot to write two-samp t-test in the beginning here. Usually just 2 would be fine because you're going to compare it to 0.05 or whatever it is your alpha is. P-values, 4 decimal places. The test statistic for 3 or 4. 4 decimal places is better. So if you're doing this, what I would like you to write down is you say to use a 2-SAM t-test and then write down your test statistic and your p-value. And then from here, we make our conclusion. Since what is what? Since the p-value is compared to alpha is what? Greater than. Remember, we're going to assume that alpha is 0.05 and our p-value is 0.16 or 0.17. Since our p-value is bigger than alpha, we what? We fail to reject. The null hypothesis. And so then that would give us a conclusion of saying, what's our conclusion? There's not sufficient sample evidence to support the claim. So there is not sufficient sample evidence to support the claim that diet 1 was more effective. So if you look at diet 1 with a mean of 2.8 pounds and diet 2 with a mean of only 1.6, it looks like diet 1 was greater. It looks like it was more, right? But based on our significance test, that greater than is not significant enough. That it's not something that's out of the ordinary. This could have happened by chance, and so there's nothing going on there. And so our probability value of 17%, 0.17, didn't give us enough evidence or enough information, not information, but didn't give us enough evidence to say that that was a significant difference. That was significantly greater. And in fact, it wasn't, because that's what our test came up with. So I'll again encompass in the highlighter what I would like to see in the test. I'd like to see the null and alternative hypothesis written out. I'd like to see what calculator command you used to make your decision. I'd like to see your decision and why you made that decision. And I'd like to see, very importantly, your conclusion in non-technical terms. So those, to me, become the 3 major components of the hypothesis test. The statement, the collecting information for the test, and then the conclusion. The conclusion that includes the rejecting or failing to reject. So if I were to put this in 3 boxes, this is one box, this is the other box, and this is the third box that would encompass all this stuff. Actually, this step over here, whether we reject it or fail to reject, kind of falls more or less in between the testing part and the conclusion part, because it's that bridge to make that conclusion. But I usually like to see it just in the conclusion part. Okay. All right. So the actual problem wasn't about a hypothesis test. The actual problem was about a confidence interval. So let's actually do the actual problem and do the confidence interval. As you can see, though, the confidence interval will be exactly the same thing. Or for us, since we're using the calculator, our confidence interval will just be the very next command in our calculator. And this is a difference between two means, so our middle value or middle term would be a mu1 minus mu2. So using the same information that we got up there, this is a 2-samp t-test, right? So what do you think the next one's going to be? 2-samp t, it's still 2 samples, and it's a t, so it's 2-samp t int. Should be somewhere down here. There you go, 2-samp t int. And since we just did the hypothesis test, all the information is still going to be there, so that's good. Oh, if not given, alpha is 0.05, so in terms of confidence level talk, it's a 95% confidence level, so let's fix that. It was 99 from the last one we did. So it's still going to be a pooled no. We're still going to assume that we don't know anything about the standard deviations for the population, so we're not going to say that they're equal if we don't know anything about it. So pooled no, and then let's calculate. So we see that we did a 2-samp t int, and then we got our results. But remember, I want you to write it with the inequalities. So this is a negative 1.282 less than. Now, since this is a difference between the two means, it's going to be mu1 minus mu2. Less than 3.6819. So we can write this down and we are 95% confident that blah blah blah. But the more interesting question, since this is a comparison between two populations, is there a significant difference between diet 1 and diet 2? No, right? Because it contains 0. So since the confidence interval, I'll start, I usually don't like using CI, but I'll just say CI. Confidence interval contains 0. There does not seem to be a significant difference. There is not a significant difference between the two diets. There is a significant difference. And that's so it turns out the confidence intervals for comparison seems to be a little bit more powerful than the confidence intervals back in chapter 7 when we first saw it, because you can actually, you don't just say, oh yeah, I'm 95% confident that this contains that or whatever. We can actually say, well, there seems to be a significant difference between these two things. These two things are not the same. All right, let's try to remember these numbers, and let's see if we can answer the questions correctly in our homework. See if we get it right. And the first thing they ask is, what is the confidence interval rounded off to 3 decimal places? So, what is it? A negative 1 point something? 282. And the second one was what? 68 what? 19? 682. I think I put 19 here and it'll still be okay. I know, but if I put 19, it should be okay, right? Sorry. Okay. Oh, it's still wrong. Oh. The digit should be 3. Now I want to go back to 1, 9 and see if it works. This is my third try, huh?
Yeah.
I hope it's right. I hope it's right. Well, they're off. Yeah, it's because they use a formula. I don't like that. You guys probably don't like it either. Well, good luck with that. Does the confidence interval show that there's a difference between them? So no, because it does contain 0, right? So let's find a no. Confidence interval does contain 0. Okay. Yeah, I'm sorry. I don't know what to do about this business when they're off. They're the ones that are off. I mean, the calculator is more precise than the tables. So if I put a 2 instead of a 1, 9, like I was trying to get fancy. Okay. Yeah. Okay. All right, so look at what they have in parentheses and follow the directions. I was trying to make a point, but I guess it backfired. Sorry. Okay. All right, we good? The part here where we assume that sigma is known is, I don't know if that comes up in any of these problems. But I'm not too interested in doing that. I can just tell you that it's a 2-samp Z test instead of a T test, and there's no worries about pool or not pooled business. If you look at the calculator and do a 2-samp Z test on it, it's just going to be straightforward where they ask you the sigmas because you're assuming that you know sigma, and then they're not going to use the S anymore, so you don't need a sample standard deviation. And then this is all they have. So if you run into one of those problems in the homework, then that's just how you're going to deal with it. I'm not going to give you that kind of a problem in the test situation because I don't think it's that pertinent in a real world situation. I don't want to do this problem, but I want to point out number 13 is an example where you have the data given to you. And so this might be a good opportunity for you to practice and work out where you would do a a 2-samp t-test where you would input all that information into L1 and L2 and use this option where they have, whether you have data or statistics. If you have the statistics, then you would use the stats. But if you have data, then you can have a calculator do all the calculations for you, including finding the mean and standard deviations for each of those samples, because the calculator can do that really quickly. All you have to do is put in the information in L1 and L2. A frequency for us is always going to be 1. Yeah. So that's another thing to remember. It says 1 in your calculator unless you changed it, which I hope you don't, because for us it's always going to be 1. And then again, whenever you see the option pooled in our class, it's always going to be no. Okay. So this will give us an opportunity to jump to the last section by skipping over those kinds of examples. So I also, since we have these PowerPoint presentation slides, I might as well just slide through them. You don't write anything down. Just look at what's up here. So this would have been the comparison, and it looks like this bar is in the wrong place. It should be X bar and not S bar. But this is what you would have had to do without a calculator. You get all your information. You don't need to do a box plot, but this is a good idea of how to do a comparison of box plots. These are the distances, by the way. Barry Bonds and Mark McGwire, that year when they were just hitting home runs like crazy, pumping up steroids and hitting home runs. Sorry. I hope I didn't offend any Giants fans or hardcore Bonds fans. Anyways, they measured the distances of how far these home runs were, and so that's what they're comparing the means between them. So they have the claim set up and the alternative, the null and alternative hypotheses, and then they need to figure out the degrees of freedom. And so McGwire hit 69 or 70 home runs, so the degrees of freedom for him is going to be 69. That's 70 minus 1, and Bonds hit 73, so that gives us 72 for the degrees of freedom. Now, between these two, they decided, they say the more conservative way of figuring out degrees of freedom is to use a smaller one. And so you would take 69 and go to table A3 and look up what your critical value would be. So they would do that, and then they would punch it into this calculator or this formula, and then they get 2.273, which we would have gotten easily with a calculator. And then they figure out where to reject and fail to reject. And then they have the confidence interval, the same business, where you would put in all this information, get the margin of error, and then subtract it to the difference of the means. Okay. This is the part I'm going to skip in terms of doing an example, but if you know the sigma 1 and sigma 2, if you know the population standard deviations, then you would essentially, instead of S, you would be using the sigmas, and then you get to stay with a Z distribution, which is easier for us to deal with. There's only one Z distribution, but if you start looking at the T distributions, you have degrees of freedom and stuff, so that gets a little bit more complicated. And then you have this thing. They give you a little flow chart. I don't think this is that interesting because, like I said, we're probably going to be sticking with non-pooled business, so you can take a look at that or not. And then I took out another whole section in the PowerPoint slides that it's not going to be that important for us. All right, let's go to the last section in this chapter where they talk about doing a hypothesis test and a confidence interval. When they say inferences for us, we should think both hypothesis tests and confidence intervals. So we're going to check out the hypothesis test and the confidence intervals for matched pairs. So we're still dealing with two populations. Maybe they're not two different populations. We're dealing with two samples. We should still technically should think about it as two different populations. But we're dealing with two samples that are actually paired up. Now, what scenario would make you pair up two things? Well, one scenario would be a before and after business. That's a common one. So maybe if you're a sprinter or something like that, you time your 100-yard dash, and then so you do the 100-yard dash several times, and then maybe just one time. So a bunch of people do a 100-yard dash, and then these people would take this special drink with some special formula, some mixed formula, whatever, steroids. And so they would do that, and then they would do the 100-yard dash again, and then they could compare the time. So each person will have 2 times, one before they took that special drink, the second one after they took that special drink. So those are going to be the pairs for each runner will have a before the drink and after the drink time that they have. And so that would be an example of a match pairs like this. And then there's a few other. Yeah. So, yeah, I guess that would be a more more common example. So a pre-test and a post-test would be another thing. So a pre-test, you take the pre-test, the same people take the post-test, and then you compare the grades and see if there's an improvement. Yeah. That probably was a nicer example than steroids or special drink. All right. So the requirements here is basically spelling out the idea that these numbers, the data sets that you're getting are going to be matched up. And so the sample consists of matched pairs. The samples are simple and random. And then this whole business that we had for our t-test again, where either the sample is large enough or the sample comes from a normally distributed, or approximately. Which, again, for our class, we'll just always assume this. Notation. So this is where I would look at your test or your quiz, and this is where I get to see whether you understood the question was actually a matched pair question, is that if you use the same notation that they're using. So the D is not so important. I'll tell you what the D is about when we actually do an example. But you want to find the mean difference, and so this is going to be mu sub D. So it's not mu sub 1, mu sub 2, it's mu sub D, D standing for the difference. X bar, instead of X bar, they use D bar. I probably would have preferred X bar sub D, but keeping with their notation, they're assuming their random variables are D instead of X, they're going to call it D bar. S sub D, instead of S sub 1 and S sub 2, or S sub X, they use S sub D to be the standard deviation of all the differences that you found. And then the N, it doesn't make sense for N sub D because the N from one sample and the N from the other sample is the same, so let's just call it N instead of sub D. So we will be finding values for D bar, S sub D, and N. Mu sub D is going to be what we're going to assume, and then we'll talk about this. This is mu sub D for us and for the sake of what we're doing, and we're not going to get too complicated. Mu sub D is always going to be compared to 0. So it's either equal to 0, less than 0, bigger than 0, or not equal to 0. But you know how back in Chapter 8 we compared it to an actual number, an actual value. Here the value that we're going to compare it to is always going to be 0. Okay, so these are going to be your important variables that you're going to use for this type of problem. Yeah, I was going to say more stuff, but more stuff is going to be needed to be said until next chapter. So the thing that's going to come up next is the test statistic, and then the confidence interval. And you'll see that it's going to be exactly the same test statistic and confidence interval as we had before, except since we're using different variables here, it's going to look different. And what I'm going to ask you to do is not freak out too much about this. It's exactly the same as the other test statistic that we've had. And so this is where I would write compare to, or compare with, section 8 dash, so 3, 4, 5, 8-5. And so it's the same t-test statistic. It's like a t-test, except everything in here is going to be the same except for the notation. So x bar minus mu sub x bar divided by s divided by square root of n. So really the same thing, right? Except d bar instead of x bar, mu sub d instead of mu sub x bar, s sub d instead of s. You know, it's the same thing. And it even has the same degrees of freedom, which is nice. Our degrees of freedom will start changing in chapter 10. So I know we've been seeing n-1, so why keep talking about degrees of freedom if it's all the same? Well, in the next chapter, we'll see the degrees of freedom change a little bit. So this is our test statistic, which might be important if I specifically ask you what is the test statistic for this scenario. But in terms of actually doing the problem, when we do the problem, we punch it into calculators, then we don't need to know the formula because the calculator is going to compute it for us. The p-values, the critical values can be found. The confidence interval is the same business. Compare with section 7-4, I believe. And our x bar plus or minus e business, where e is equal to t sub alpha over 2 s over square root of n. So it's going to be the same, again, the same thing with the same table A3, degrees of freedom. This is a t-test. This is a t-interval. In fact, in the calculator, we're going to be using t-interval and t-test as well. So the biggest difference here is that we're taking this from a context of 2 sample, but it's not really a 2-sample t-test. It's really just a regular 1 t-test, and we're combining the 2 samples into 1. That's our biggest key. All right. I think that's all we need to know before we do an example. So here's their example, the forecast. You can look at that. We will break from this and go into our homework and find a homework problem to do. We are in section 9.4. And a lot of times the data, they'll actually give you the raw data. So this is going to require you to punch some stuff into your calculators. I'm going to see if I can pick one that has less than 8. 1, 2. I guess they all have 8. All right, these are easier numbers to put in. So this is a confidence interval problem. Let's prepend it with a hypothesis test problem. I'm sorry, you guys already write it down? Can I change the problem? Something more interesting. Something that actually has looks like more like a real world problem. Now let's do this one. This is a test that you were talking about, Monica. So what we'll do is we'll do the hypothesis test. This problem is actually asking us to do a hypothesis test, and then we'll also do a confidence interval as well. So, see what it says here. A control group of 8 students were given the same test twice to see whether retaking the test affected their scores. This is almost like a pre and post test. Below their scores on their first and second attempts. Test a claim that the difference have a mean of 0. The difference have a mean of 0 using a 0.05 significance level. What do the results suggest? Have a mean of 0. So in terms of the notation that we were asked, the first thing, the notation that was all listed down, you guys copied it down. The first one was D. They called it D. The D would be random variables, a set of random variables, so it would actually be the numbers, and the numbers would be the difference between these things. Now I'm going to write down the difference for a few of them, but I don't want to do the whole thing. But if we take the difference as the first minus the second, we'll do that subtraction. This is probably not a good subtraction because I'm going to get a bunch of negative numbers, but I'll do it that way anyway. So negative 60, what's this one? Negative 50. I'm just going to put dot, dot, dot because I'm going to have the calculator do this work for me. But that's really, I just wanted to show you that when they say D, they mean a list of data points. Just like X is a random variable that has a list of things, D is the same way. So D would be all these differences. We will use our calculators, and we will actually use a regular t-test thing that we've done before. But I would be basically looking out for the claim and all that stuff. So let's, before we pull out our calculators, let's take a look at the claim business. What should our claim be? So the claim in words is easy enough to copy and rewrite down. The difference have a mean of 0. And maybe we want to include the difference between the first and second test. Has a mean of 0. This actually is an easier claim to decipher. Sometimes they ask you whether there's an improvement or not, and that claim in mathematical symbols would be a little bit more tricky to decipher. But let's see if we can do this one, and I'll see if I can do another one just to set up a claim. Anyways, the mean difference, mu sub d. This is where the mu sub d comes in, and it becomes important to use that proper notation. Is what? Is equal to, less than, greater than, not equal to? Is equal to, has a mean of 0, so it's equal to 0. So this will become our null hypothesis, right? And your alternative hypothesis is the not equal to business. So there is our information. The next step is to gather, well, the first step would have been to gather the data, but then gather the statistics, but we don't have the stats, we have the data. So let's punch it in our calculators. Hopefully this won't take too long. And so this is, you could do it any way you want, but this is how I'm going to suggest that you do this. The first and second one will go into L1 and L2, and it will eventually compute the differences in L3. So here's how it's going to go. I'm going to clear out my L1 list, and I'm actually going to clear out my L2 list as well. I could clear out my L3 list, but I'm not. I'm just going to overwrite it. We'll deal with that later. So L1 will be the first numbers, so that's 510 and 580. So it's a little tricky. I'm reading it sideways, but I'm writing it down. The calculator's having it written downwards, so just make sure you're okay with that. So we got 500, 630, 440, and 520. All right, got 8 numbers down. I'm going to right arrow real quick to L2 and write down the second exam scores. 570, 630, 560, 690, 480, 660, 460, and 550. Now, one of the important things to make sure is that your list is the same size. If your list is not the same size, you forgot something, and it's going to give you an error. So, my list is the same size. I'm fairly confident that it's all typed up correctly. I hope it is. So this is now where we find the difference. So I'm going to go to L3, and I'm going to put my cursor up on L3 so that that thing down below here says L3 without a parentheses in there. Doesn't say parentheses 1, it's just L3 equals, right? And I want L1 minus L2. So I'm going to say, type in L1 minus L2. Okay? And when you press enter, you'll see that it's going to get populated. The first 2 numbers should be negative 60 and negative 50. And then you can march along and see that everything else should be correct. And if you want on a test or for yourselves to make a note that, well, my first list I put that in L1, my second list I put that in L2, and my L3 was equal to L1 minus L2, and then I get this new list that I'm not going to bother writing down. Dim, mismatch, data type. Oh, minus sign. The minus sign, not the negative sign. Minus, maybe. So a common error would be a dimension mismatch, which means one of your lists is not the same size as the other. The other one, type mismatch, might be putting in the correct negative sign. That work? No? Work? Okay, so once we get here, this problem becomes a problem back in Chapter 8. This problem becomes a one sample problem because we've combined the 2 samples into 1 sample, and now it's just a regular t-test. So that's exactly what we're going to do. So after you've populated your list with the correct differences, you would go to Stat, Test, and do the t-test. We have the data in L3, so you just have to remember that the data is in L3. And so our input is going to be data. Our mu sub 0 is going to be whatever you have, the number that you have in your null hypothesis, which is 0. So if you have something else other than 0 there, just make sure you type in a 0. And then the list was in L3. It got transferred to L3, so make sure you're using the appropriate list, so second function and number 3. Frequency is always going to be 1, and then your alternative hypothesis for this particular problem is a not equal to. It could be different for different problems, but For this one, it's a not equal to. So this is all our input, our information put in, and we're actually going to use a t-test and just have it calculate. So this is where it's going to be important for you to use your appropriate notation. And when you do this t-test, it's good for you to write down as much information as possible. So you can say a t-test, and then your list is going to be an L3, which you got by subtracting L1 minus L2. That piece of information would be good for me to know. That's exactly what you're doing. I don't necessarily need to see that, but I think if you write it down, it would just be a good reinforcement. And that's really the only thing I need to see here. And then your results would be your usual test statistic, which is a t-test statistic. It looks like it's a negative 1.99. Your PV is going to be a 0.0867. And since we didn't have all this information before, it might be good for you to write down the statistics that they computed for you. Now, the statistics that they computed for you says x bar equals, sx equals, and an n equals. But remember our notation changed, right? Instead of x bar, we use what? We use d bar, and that was equal to, and this is equal to negative 22.5. Instead of s or sx, we use s sub d, which is a big standard deviation, as 31.959, let's call it 96. And then our n is equal to 8. So really what we're focused on is the test statistic and the p-value, and since we are not bothering with a table, I don't want to have to find critical values, so I'm going to focus on the p-value, and the p-value is what compared to alpha? This looks like it's greater than alpha, right? So we had alpha is 0.05 or whatever it was. 0.05 significance. Since 0.08, or it's actually closer to 0.09, is bigger than 0.05, we what? We fail to reject the null hypothesis. Okay. Oh, I didn't put claim here. Which one was my claim? The null hypothesis was my claim. It's always nice to mark down which one your claim was, so that when you go through that last step where we write down in non-technical terms, we ask ourselves, does your claim contain a condition of equality? And if I have it labeled as my claim, then that's easy for me to get. So yes, it does contain a condition of equality. Did we reject the null hypothesis? Nope, we failed to reject it. So in that flow chart, we're in the second box. And the second box says something to the effect that we what does it say? Okay. There is not sufficient evidence to warrant the rejection of the claim that the mean difference is 0. Okay, so let's see what they're asking for in this actual problem. We did more work than they're asking for, but this is the amount of work that I would expect in a test or quiz situation for me. But let's go to the homework. Can a null hypothesis be rejected? What did we do? We didn't reject it, right? We did not, so that's no. The test statistic falls in the critical region. No, the test statistic does not fall in the critical region. We didn't do that test statistic business, but which one should it be? Okay, if it falls in the critical region, then you have to reject it. So B is not the answer. So it has to be D. Okay? So that's our criteria. This suggests that it appears likely that the scores are the same after retesting. What do you guys think? Okay, let's read this information here. There is not sufficient evidence to warrant the rejection of the claim that the mean difference is 0. We didn't reject that the mean difference is 0. The mean difference is 0 means that there is not a significant difference between the two things, right? And we didn't reject that. So it suggests that it suggests that it appears likely that the scores are the same after retesting. It suggests that it appears unlikely that the scores. Is it likely or unlikely that the scores are the same? I think it would be more likely because we didn't reject that, right? So it seems like they appear to be the same. So the words are really tricky. You have to read it carefully, and you have to have a full grasp understanding of the words in English at that. So if this is your second language, that makes it a little tougher. So just kind of read it carefully and walk through it in your head and translate it to your own language and see if you can understand it. But the appears likely, unlikely, that that business is really tricky. So just I guess be careful with that. Okay. The last thing I want to do is a confidence interval for this. Well, I think this is it's kind of worth adding to our notes here. So the last thing I want to do is a quick confidence interval for this, and the confidence interval will pretty much be the same thing as the confidence interval in Chapter 7. So this is a regular t-test, so you would imagine that our confidence interval would be a regular t-interval. And it is going to be just that. So if we go to stat and test, I think that would be number 8, right past the z interval, is the t interval. So we just run through that, and we have the data in L3 at a 95% confidence. We'll stick with the 95% confidence. We'll do the calculation. And this is where it becomes really important that you write this with the appropriate symbol. So it's negative 49.22 less than something less than 4.2191. It does contain 0, right? What is that symbol that goes in between? Mu sub d, right? The same as in the hypothesis test. The null hypothesis, this is going to be the symbol for mu sub d. Contains 0, doesn't seem to be a difference, and that's the same conclusion that we got from before, but it's significantly the same. Oh, the screen right before it. So list is in L3, which if we just did a t-test right before that, it would still be there. 95% confident if we had it the same. And so it's relying on your comfort level of chapters 7 and 8. And if you're comfortable with chapter 7 and 8, this was a piece of cake. If you're still having issues with chapter 7 and 8, do the homework. It's due tomorrow, so do the homework tonight or whenever before tomorrow. And then hopefully, the more you do these hypothesis testing and confidence intervals, then the easier this chapter is going to be for you. Okay. All right. So that's it. We did it. We actually finished chapter 9. Whew. So I don't have to do any extra recordings, which means the recordings are going to be extra long. I encourage you to go visit those YouTube videos or the iTunes U to make sure you understand the step-by-step process. And the variety. There's a lot of variety here.